Great. Hi, everyone. Okay, so my name is Ylva Ferstl, and I'll be presenting the paper Expressive Gesture Generation from Speech Through Database Matching. And my co-authors are Michael Neff and Rachel McDonnell. So conversing virtual agents are nowadays found in numerous applications, as we probably all know, being at this conference, and animating their nonverbal behavior makes the agents a lot more lifelike and engaging. But when we handcraft these animations, this is very time consuming and it requires skilled animators. So by finding methods to automatically generate these animations for conversing agents, we can scale to much larger amounts of new content at low cost. For example, for video games where we then only have to bring in a voice actor, or they can do it from home with a high quality microphone with no need for motion capture. So our goal is basically to automatically generate such co-verbal gesture motion, as you can see here, only from speech audio input. And previous work has used rule-based approaches with explicit phrase-to-gesture rules, statistical modeling of some likelihoods of some speech features co-occurring with some motion features, as well as now a lot of machine learning approaches. For example, Levine and colleagues here represented gesture motion through 6 kinematic features and combined a hidden Markov model with a conditional random field to model gestures from speech animations that they then selected from a library, a motion library of 12 minutes of segmented motion. And here you can see a sample.
I credit it to the fact that I, at least for a very long time, probably taught every single undergraduate major. There was no, it was virtually impossible for anyone to be a major in CS and to not take the class I taught them, because I was the only instructor, and it was advanced enough that even our best students probably wouldn't skip it.
Okay, so that
adventure, even
that was from 2010. In a statistical modeling approach, Yang and colleagues used motion graphs last year to model dyadic conversation behavior, and they used a 30-minute data set. So when they were synthesizing new gesture behavior, they basically searched a path through the motion graph based on some speech constraints that were associated with the motion. And here's a sample of this.
Tell me a little bit.
I don't know, you're doing your acting face, so
Oh,
yeah, so clearly something's up. What do you want to talk to me about?
I just I wanted to ask why. Oh,
Yeah,
that's right.
Okay. And then generative machine learning approaches produce entirely new motion instead of working with a library of segmented motion. For example, Kucharenko and colleagues used an autoregressive feed-forward neural network for this last year, trained on 4 hours of data. And here's a sample of that as well.
One scene where I guess it was kind of out of place, but I still quite liked that it was there, where it was kind of like a weirdly comedic.
Okay, and finally, Rabol and Christian used a generative adversarial network trained on 100 hours of YouTube data. And unfortunately, this has no sound. So generative machine learning approaches often have the problem of suffering from a regression to the mean pose. So they produce overly smooth motion with a relatively small range and fail to capture the variety that is present within the original data set. So in this work, we combine machine learning to establish the speech-gesture relationship with database sampling to ensure a defined gesture form and high variety. We use 2 datasets representing different speaker styles. So the first Trinity speech-gesture dataset here is on the left. That represents the 4 hours of data that were also shown in the previous clip that I showed for Kucharenko and colleagues. And our new dataset, the second Trinity speech gesture dataset here on the right, consists of 6 hours of a different speaker. And as you can see, the 2 speakers exhibit a very different, very distinctly different style, with speaker 1 moving around a lot and making it much more difficult to separate his arm motion, so his gesture motion, from the rest of his body dynamics. While speaker 2 shows a much more grounded stance, and it's easier to segment his upper body motion. And here's just a sample with sound.
And I remember I was like, right, when he gets off that bike and puts it back up, I'm going to go on it, and I'm going to go down the hill and go down to my granny's. I thought, because I'm big enough, I can do it. If he can do it, I can do it. So I remember I went into my mum. She was in the kitchen. She was like cooking or something, or she was just kind of cleaning up or whatever. And I walked in and I asked her for a cheese sandwich, because she used to make this like gorgeous homemade bread, brown bread. She still does, and it's beautiful. So I asked her, could I have a cheese sandwich? And that I was just telling her that I was going to go on the bike and going to go down the hill.
Okay, so this is our new speaker, and we are releasing this dataset to be open source the same way as the first Trinity speech gesture dataset. Okay, so using a method we previously presented, we automatically segment all the motion data into individual gestures and add them to a gesture database. And by combining our two datasets, this yields over 23,000 individual gestures for the database. And then we design an end-to-end gesture generation system where instead of predicting motion directly from the speech, we estimate motion parameters that describe the expressivity of a gesture and then search our database for the gesture that best matches these estimated parameters. And the motion parameters specifically are the velocity of the gesture and the initial acceleration, as well as the size of the gesture, the arm swivel, which is the distance of the elbow to the torso, basically, and the hand opening, so how open or closed the hand is. And these can all be automatically computed from the motion data of a gesture. So for each gesture in our segmented database, we hence also compute these motion parameters and store these values with the motion data. And now let's look at this pipeline in more detail. So we first use the speech pitch from an audio input to determine when we want to generate a gesture. So by analyzing the pitch, we find the emphasized segments in the speech. So the timings of the pitch peaks indicate when we would like to generate a gesture. Specifically following a previously found rule that gestures either precede or coincide with the associated speech peak. So the peak of the gesture comes either before or with the speech peak. We set gestures to be 55% complete at the detected pitch peak. And we can tune the sensitivity to the peaks in the speech pitch, and by that affect the frequency of gestures for the animated character. So based on the detected pitch peaks, we take the surrounding speech segments and extract a wider set of prosodic features, and these are then used with our machine learned models to predict parameters from these prosodic features. So predict the 5 gesture parameters that you can see here. Next, we search the database for the gestures that best matches these 5 predicted parameters and insert them into the associated location in the gesture sequence. And then finally, we link all the sampled gestures by synthesizing transitions between these gestures. And for now, we use very simple motion blending. And you can see the motion blending technique here used to link the gestures. On the left, you have the full ground truth motion produced from the motion capture. And on the right are the individual ground truth gestures linked with synthesized preparations and retractions, as well as having some added idle torso motion and head motion. Okay, so now let's see some samples that we generated with our method for the 2 different speakers.
I'm massively into traveling and stuff like that, so whether it's nationally or internationally. Some of the best experiences that I've ever had in my life have actually been my trips nationally. So where I go every year with my family and my friends as like a tourist attraction type thing. So yeah, so much amazing stories that I could honestly harp on for hours and hours and hours about Kirklow. But that Kirklow in itself is my childhood, it's my upbringing. It's one of the nicest and best places I find in this country to go visit.
That's kind of the trap from studying philosophy, is that I end up having to include it in everything that I do. Like, I swear to God, there's a few books or things that hopefully will turn into books in the works. Reality where I'm constantly wanting to be somewhere else, and that's what I was scared of, because I was like, the classes aren't that fun. I hate the way that we wake up in the morning.
Okay. So then we conducted 2 perceptual studies for evaluating our gesture generation system. So participants watched the video clip as you just saw now and rated the question, how appropriate were the gestures for the speech on a standard 7-point Likert scale. And in our first study, get the laser pointer. In our first study, we compared our method of gesture placement and selection to randomized gesture selection and placement, as well as the ground truth gesture selection and placement. And these were all generated with synthetic transitions to produce the same kind of appearance. And we used both our new dataset and the first Trinity speech gesture dataset. So these are the results for the 2 different speakers. And the y-axis here represents the number of responses. So our results here confirm the validity of our gesture selection method. So our method was rated as matching the speech significantly better than randomly selecting gestures from the database, where randomly means that gestures were selected agnostic to these predicted motion parameters. And while comparison to the random condition here may conflate effects of gesture selection and gesture timing, we actually investigated this in a preliminary study in which we again compared to the ground truth to a condition with ground truth gesture timing, but gestures for these timings were filled with our method. So this is just completely our method here called matching. Then the ground truth gesture timing, but with randomly selected gestures. So we kept the correct timing, but we just filled any gesture that would fit in there, completely agnostic to which parameters might be best, which motion parameters might be best, to a condition with random timing and randomly selected gestures. And we showed that the correct gesture timing alone, so the difference between baseline 1 and 2, is not sufficient to increase the perceived speech gesture match, actually surprisingly. So, but matching our gestures to the speech via our parameters did increase the speech gesture match. So we can confirm that in the study here, the reason for our superior performance was not just having predicted better gesture timing. Okay. In our second study, we compare our method to state-of-the-art machine learning models, namely the 5 entries from last year's Expressive Gesture Generation Challenge. And we again also include the ground truth motion, which is the full motion capture without the synthetic transitions, which is here. And then the ground truth gestures with synthetic transitions right next to it. And then mismatched motion, which is real motion, but paired with the wrong speech segment. And then the 5 Genia entries. And the Genia challenge, unfortunately, only used the first Trinity speech gesture dataset. So the second evaluation is just restricted to speaker 1. So the one you saw kind of moving more animatedly. Okay, so the results of our second evaluation show that our method here produces competitive results to state-of-the-art machine learning models with respect to the perceived appropriateness of the gestures for the speech. And specifically, the results showed that the SA Genia entry here was rated significantly lower than all others. SC here was rated significantly higher than SB, and all the other differences were not significant in the group that I'm highlighting here. And while our method can be distinguished fairly easily from the other generated motions through these procedural transitions, these more maybe robotic-looking transitions between the gestures, it was still rated on par or superior with the compared generative approaches. And here you can see what here can see what I mean by that it's easily distinguishable. So on the left is the Genia entry SD, highlighted here, which was rated most closely to ours SD. So the synthetic transitions did not apparently take away much from the performance. And indeed, we actually found that the synthetic gesture transitions did not impact the speech gesture match, indicating so the full ground truth motion versus the ground truth gestures with synthetic transitions were not significantly different from each other. So that indicates that matching individual gestures to the speech produces valid results even when that changes the overall motion style of the speaker. And in our approach, we generate only arm gesture motion with some auxiliary idle animation for the torso and head. And we think that that actually yields a motion style closer to speaker one, so the one with that retains a more firm stance and produces more isolated arm gesture motion. So we think our method produces particularly suitable results for this speaker. However, as I said, in the Genea models, the Genea models were only trained on the first speaker. So unfortunately here in the second evaluation, we could not evaluate this. But I can illustrate this with an example for each speaker.
About the text, just to make it about the conversations, because I don't know, it's just for whatever reason, I just wanted to, instead of having a player's show that was trying to have all these in-jokes,
So you can see that the ground truth has a lot more motion than the generated, whereas here for the second speaker, it's more
all
similar.
different stuff in relation to animals like cows, chickens, horses, all that sort of stuff, because they all had that down there in the place. And obviously because it's such a kind of a scenic type of place. I mean, it's absolutely gorgeous down there, especially when the weather's good. I mean, it's just absolutely beautiful, especially along Ballinesker Beach itself is just, it's for me, in my point of view, not being biased, but I think it's the best beach in the country. It's the nicest sand, the clearest water, and it's actually really, really warm and nice.
Okay. So to conclude, we present an end-to-end system for gesture generation from speech audio alone, and by using combination of machine learning and database sampling, we can ensure a defined gesture form, avoiding the common pitfall of overly smooth or lethargic motion produced by some generative machine learning models. And our gesture-by-gesture approach allows for modifying the expression of individual gestures. So while most machine learning approaches generate continuous motion and therefore lack the freedom of manipulating individual gestures, our system can be combined, for example, with the method proposed by Sun Lu and colleagues this year for stylizing gestures. We also think that our system may be easier to integrate into existing state-based frameworks used by game developers. And finally, just want to point out again that we release a new data set of 6 hours of high-quality 3D motion and audio recordings of completely spontaneous and natural speech, as well as our proposed segmentation into 23,000 individual gestures. And we think that also our segmentation into these individual gestures facilitates a deeper analysis of gestures themselves, as well as the speech-gesture relation. In future work, we'd like to address the question of shape-describing gesture parameters, since here we only use these expressive parameters that don't show really what form the gesture is describing, as well as including semantic speech information for modeling these parameters, rather than just the prosodic speech audio, in order just to improve the gesture selection. We also want to explore some alternatives to the current motion blending. So for linking the individual gestures, just to make the overall realism higher of the motion. And then finally, we also want to explore using a learned representation of this motion capture database for more efficient storage and retrieval, such as in Holden's learned motion matching. Okay, so that's it for my presentation. Thank you very much for listening. And please, if you have any questions, you can give them to me now.
So, thank you, Ylva. That was really nice. We have a couple of questions currently in the Q&A. I'm going to start with the audience. I have a couple of questions myself. So Liazu says, would you consider adding modules that could detect keywords from speech to add a wider range of variations to gestures?
Yeah, thank you very much for that. That is definitely something that we've explored and we're also looking at for future work. The problem is a little bit the amount of data that we currently have for these conversational gestures. So we have to kind of pick very carefully a set of keywords that really would occur often enough in meaningful ways to be able to model them. We weren't yet able to do that, but it's definitely a good point and kind of in the already tried but also future work section.
Thank you. Nadia, did you want to ask your question?
Yes, thank you. Thank you for the nice presentation. I have a question about the papers you have presented in IVA in 2020. What is the difference with this one? What is the new contribution you have done from this paper?
Okay, so in IVA, for people who don't know it, it's basically the part of the pipeline that takes prosodic features and estimates motion parameters. And this is an extension of this work. So basically the main difference is really just that this is a full working pipeline. So we decide, for example, the speech segment from which to extract the prosodic information. We need to decide that now just based on a speech audio, versus in IVA we had the motion segmentation. We knew here and here was a gesture, and we just take the audio that is associated with that. So I think that is one of the key ingredients here. And yeah, then obviously we put it into a full pipeline by linking the gestures, etc. But yeah, it's definitely heavily based on IVA.
And in the other paper in computer graphics in 2020 also, where adversarial gesture generation with realistic gesture phasing. What is different also with this paper now?
Oh, this one, that is very different. So in computers and graphics, we basically just take the one part, which is in computers and graphics, a part of the paper was training a model that could take motion capture data of our data sets and predict where the gesture boundaries are. And this is basically the only part that we use here. So we use it to segment the motion, but otherwise the computers and graphics was used a generative adversarial network to produce continuous motion rather than drawing from a database. And like there was nothing with motion parameters, so it was completely agnostic to that. It was just trying to implicitly learn the relation between speech input and motion output. So yeah, completely different model, and also the results qualitatively very different. So for the computers and graphics results, I would never put that into a deployed application, whereas these results are getting there slowly.
My last comment, thank you to answer the question. My last comment is about the validation. You have the ground truth and of course the calculation and simulation. So the ground truth, you have preferred to make a 3D character similar to what you have found as a result. You didn't like to compare with real people? Because I didn't
with real people, or with more realistic characters.
Yeah.
Okay, so the one reason is, for example, we wanted to mainly keep it close to Genea, but we actually ran a study on this, a perceptual study on whether the appearance of the character matters of how well the speech and gesture go together. Will be this year's IVA, so the results are not published yet, but we showed that it doesn't actually affect the speech gesture match. So whether we have a robot character or a highly realistic humanoid character did not affect how people perceived that the speech and gesture, how well they were matching. So I don't think that that really influenced the results. And secondly, in our in the preliminary work that I pointed out, where we compared to two baseline motions, where we compare with gesture timing, we did have a slight, like a more realistic character. It was the humanoid, the Brad character from the Virtual Human Toolkit. So we did have a humanoid character there, not super high.
My question was more, instead of taking a virtual character, I was wondering why it was not simply a real person saying the same.
Oh.
You understand? You speak the sentences and the generated one speaks the same and we can see. That was more my question.
So basically validating on a new speaker, is that the question? I'm not sure I understand. So I mean,
I think the question is of a real speaker.
Yeah. But as in, I don't know how it is different from the speakers that are in our data set. I'm not sure I understand the question.
Anyway, thank you very much for the answers.
Okay, sorry that I didn't understand this one.
Okay, so I just have one
Maybe
more
we can
question.
discuss it offline.
I just have one more question from the floor, and then we'll finish there. So Leah also asked about how you deal with gestures which cross over. So in certain regions, I mean, you know, just in English, different regions, different speech will create different gestures, and you're going to have different gestures which mean different things. As you expand, how do you feel that's going to, deal with different cultural groups, and then eventually get to different languages? How do you feel that's going to work?
Again, this is super interesting areas for future work. The problem is really the data limit, like the limitation in amounts of data that we have here. So we're unfortunately stuck with basically the two data sets our group recorded, because there isn't really anything out there. I think there's some more promises now in that field with harvesting YouTube data. It's just that on YouTube data, a lot of it is much more rehearsed speech, so not really conversational, spontaneous. But yeah, I think before we can make any statements about that, we would have to have a data set like that and be able to look at that, and then hopefully we can train a much more informed model that can detect much more variety in the speaker that is speaking. Maybe we can detect the language, the personality. But yeah, I think that's.
It's very complex.
Yeah, it is. It is super complex. It's a difficult problem.
Okay, so thank you very much.